Hello everyone, my name is K.Chinmay, studying from Sri Venkateshwara College of Engineering. My campus ID is 23CS1715 and the course title is Mathematics for CSE stream. In this video, we are going to discuss about the topic vector integration. Introduction to vector integration, where mathematical concepts meet practical applications. Explore the fundamental principles and techniques that enable seamless analysis and synthesis of multidimensional data. Line integrals. Line integrals are the fundamental concept in vector calculus, representing the integral of a vector field along a specified curve or path. They are used to calculate quantities such as work, circulation, and the flux along a curve. Line integrals are defined as the sum of dot product of the vector field and the infinitesimal displacement vector along the curve. They can be used to calculate the work done by force field, the flux of a fluid flowing through a surface, or circulation of a vector field around a closed curve. The value of line integral depends on the path taken, and the various properties of line integrals, such as path independence and the fundamental theorem of line integrals, are important in vector calculus. Properties of line integrals. Path dependent. Line integrals depend on the path taken between the endpoints, not just the endpoints themselves. Conservative vector fields. For conservative vector fields, the line integral is independent of the path and only depends on the initial and final points. Change of variables. Line integrals can be transformed using a change of variables, allowing them to be evaluated more easily. Surface integrals. Surface integrals are the fundamental concept in the vector calculus, allowing us to compute the flow of vector field over a curved surface. They are essential for understanding the behavior of physical quantities like electrical flux and fluid flow and more. By integrating the dot product of vector field and the surface normal over a surface, we can gain valuable insights about the overall behavior of the field in the region. Properties of surface integrals. Orientation dependence. Surface integrals depend on the orientation of the surface, unlike line integrals, which are independent of direction. Additive property. The surface integral over a region can be computed as the sum of integrals over non-overlapping subregions that make up the full region. Linearity. Surface integrals exhibit linearity, meaning the integral of a linear combination of functions is same as linear combination of the individual integrals. Green's theorem. What is Green's theorem? Green's theorem is a fundamental result in vector calculus that relates a line integral around a closed curve to double integral over an enclosed region. It provides a powerful tool for evaluating planar vector field integrals. Applications of Green's theorem. Green's theorem has numerous applications in physics and engineering, such as calculating work done by force field and the flux of vector field and the circulation of fluid. Formulation. The theorem states that the vector field F is equal to P, Q and a simple closed curve C bounding a region D, and the line integral of F around the C is equal to double integral of the divergence of F over D. Intuition. Intuitively, Green's theorem allows us to break down a complicated line integral into simpler area integral, which can be easier to evaluate. This transformation can simplify many challenging vector calculus problems. Stokes theorem. It is a powerful result that relates the circulation of vector field around a closed curve to the flux, the curl of a vector field through the surface enclosed by the curve. The powerful connection between the line and surface integrals allows us to simplify the calculation of complex circulation integrals. Divergence theorem. The divergence theorem, also known as the Gauss theorem, is fundamental result in vector calculus that results the flow of vector field through a closed surface to the divergence of the field within the enclosed volume. It provides a powerful tool for transforming volume integrals into surface integrals and vice versa. Applications of vector integration. Electromagnetic field analysis. Vector integration is used to calculate the magnetic flux and the electrical fields in electromagnetic devices like motors, transformers, and generators. Fluid dynamics. Vector integrals describe the flow of fluids, allowing the engineers to model and analyze the complex phenomena like drag, lift, and circulation. Gravitational field mapping. Vector integration is essential for mapping gravitational fields around the planets, stars, and other celestial bodies, aiding in space exploration and astronomy. Thermodynamics. Vector integrals are used to calculate important thermodynamic quantities like heat flux and work done and helping engineers design efficient energy systems. By this, my presentation comes to an end. If you find this video informative, please like, share, and subscribe. Thank you.